Okay, welcome back everyone. So in this video we're going to look a little bit more at RL circuits and also the energy stored in the magnetic field of an inductor. So just a bit of review that we talked previously about what happens when the switch is closed for an RL circuit, and that was basically that the inductor is going to keep the current from increasing as rapidly as it normally would. And we also said that when we open the switch of an RL circuit, that the inductor plays the role of maintaining the current to try to keep it going. Remember that in both cases, what the inductor is doing is it's opposing a change in the status quo. So we can sketch graphs of what happens in the RL circuit when the switch has just closed, and if we label this as I max, that is the current that we're going to reach eventually, and we reach it via an exponential function. So remember, this was basically I max times 1 minus e to the negative t over tau. Tau is that inductive constant. Now, VR, the voltage in the resistor, is going to be basically the same, okay, because VR is basically going to be equal to I times R. So you take whatever the current is, multiply it by resistance, it'll have the same shape as the current graph. But the voltage across the inductor is going to be different, because that, as we talked about previously, is going to be negative L di dt. But di dt is just the slope of this graph, and after a long time, the current is no longer increasing. So VL actually starts at a maximum value and decreases. Okay, so basically we're talking about the slope of the graph of I. Okay, now when the switch is opened, this is going to be essentially the same thing as before, except I max is going to be, the current is going to be decreasing from I max down to 0, and that was our equation. I is equal to I max e to the negative t over tau. And if we take the slope of that, we're going to find that basically the voltage across the inductor is going to slowly decrease as well. Okay, because remember that this is equal to negative L di dt. So even though the current graph has negative slopes, you multiply that by a negative sign, you're going to get positive values for the voltage across the inductor. And across the resistor will be pretty much the same. That's going to be equal to IR, so it's going to behave exactly the same as the current. Okay, so that's conceptually what these graphs are going to look like. So now let's look at a couple of examples. So let's say we have a 12-volt battery and we connect it in series with a 10 ohm resistor and 2 Henry inductor. How long will it take the current to reach 50% of its final value? Now the final value is what we call I max, which is E over R, and that E is 12 from the battery. So 12 over 10 is just going to be 1.2 amps. Now that number is not important because we can just solve I is equal to I max times 1 minus e to the negative t over tau. And of course tau is L over R. L over R in this case is 0.2 over 10, so it's just, or 2 over 10 rather, so it's just 0.2. Okay, and so what we want is for this system to reach 50% of the final value. So we want I to be 0.5 of I max. So we can put that I max here, and then 1 minus e to the negative t over tau. Now 1 over 0.2 is just 5, so it's e to the negative 5t. Okay? So then we cross that out, we'll bring the 1 to the other side, So negative 0.5 is equal to negative e to the negative 0.5t. Get rid of those negative signs, and let's take the natural log of each side to get rid of the e, and so we'll just have negative 0.5t. So the time is going to be negative natural log of 0.5 over 0.5. There's other ways that you can write this. You can get rid of that negative sign by just writing natural log of 2 over 0.5. But either way, that's going to be about 0.139 seconds. Now let's think about this and see if this makes sense, because we know that in the space of one time constant that the current is supposed to increase. My graph is not perfect. Tau is probably over here. So if this is I max, 1 tau is to get to 0.63 of I max, so 63% of its final value. And tau is 0.2 seconds. So it makes sense that at 0.139 seconds, we're at 50% of I max, whereas at tau equal to 0.2 seconds, we're at 63% of I max. So conceptually, our answer makes sense. Okay, let's try another one. How much resistance is in an RL circuit in which L is 2.5 henries and the current increases to 90% of its final value in 3 seconds? So we'll just set this up. Again, we have I is equal to I max times 1 minus e to the minus r over L times t. We can write it out this time. And let's see here. We can then put in 0.9 is equal to 1 minus e to the minus r over 2.5 times 3. Okay? So 0.9 is equal to essentially 1 minus e to the negative r times 1.2. And we can solve that. So 0.1 is equal to e to the minus 1.2r, and you can solve that pretty easily to get r is equal to 1.92 ohms. Okay, now let's do another bit of a check here. And so what we're told is that we're getting to 90% of the final value in 0.3 seconds. Okay, so here's one thing that we can look at. So tau RL is going to be L over R. So 2.5 over 1.92 is going to give us 1.3 seconds. And that's where the current is getting to 63%. So it's reasonable to think that the current gets to 90% in 3 seconds. Because remember that once we hit tau, we're most of the way there, and the rest of it is a fairly slow climb as it exponentially approaches I max. Okay, so these inductors store energy in them. And the energy that's stored is equal to 1/2 L I squared. And again, this might be one of these things where you're like, wait a second, how could that possibly be units of energy? Well, let's try and break this down real quick. And as we talked about earlier, E is L di dt. So that means that the Henry, or inductance, basically is volts times seconds over amps. Okay, so volts times seconds over amps, and then we want to multiply that by amps squared. So that's going to give us essentially volts times amps times seconds. Okay, now I actually recognize that because remember that power is equal to VI, which is watts. So that means that volts times amps is watts, and watts times seconds is joules. So once again, through the power of units, we can see that an equation that I'm not proving could actually be reasonable. Okay, so this is the equation for the energy stored in an inductor. So let's try an example problem. we want to find the energy associated with the magnetic field of a 200-turn solenoid in which a current of 1.7 amps produces a flux of 3.7 times 10 to the minus fourth Tesla meters squared. So first we start with our definition of EL, because we're going to need this, is negative L di dt. But we also recognize that this is equal to negative N d flux dt from Faraday's law. And so what we can do here is we can actually set these equal, and this means that negative L di dt is equal to negative N d flux dt. And here's a cute little thing that you can do, aside from making those both positive. If I have dt's on both sides, I can pretend like they're not there. So I basically have L di is equal to N d flux. And then if I pretend like di is really a large scale change, well, then I can get rid of those deltas by saying that I naught and flux naught is equal to 0. So Li is equal to N flux. And that's a little trick that I did there. Okay, so that allows me to calculate the value of Li. And because magnetic energy is equal to 1/2 Li squared, that's actually equal to 1/2 Li times I. So that's a nifty little trick, because I have the number of turns and I have the flux, and if I multiply those together, I get 0.074, whatever that unit is. I think we said in the previous slide that it was volts times seconds, which makes sense, I think. And if we plug that into here, 1/2 times 0.074 times 1.75, then we get the energy stored in this inductor. Okay, whoops, let's go back a second just to make sure we're all good with this. Okay, so finally, one more example, and we're going to look at an RL circuit where we have a 4 Henry inductor and a 5 ohm resistor, a 22 volt battery at t equals 0. We want to find out what energy is stored in the inductor when the current is 0.5 amps. At what rate is energy being stored when the current is 1 amp? Okay, so this is where things get a little bit tricky, okay? Because we can calculate the energy pretty easily. That's 1/2 Li squared, and that's just 1/2 times 4 times 0.5 squared, so that's easy, that's half a joule. Okay, but the rate that energy is being stored is actually the power, okay, because power is joules per second. So in order to do that, we take the voltage of the inductor and we multiply that by the current. Now the reason we can do that is that P is equal to VI. So this is just another application of that. So the inductor has negative L di dt times I. So this is the expression that we have to evaluate in order to determine the rate at which energy is being stored. Now I'm not going to do the units because I don't want to make this video any longer, because we're going to have to actually calculate a few things out. First of all, we have to find the current, okay? Or we have to find the time to get to a current of 1. So we apply our equation, 1 minus e to the minus r over L times t, and I'm not going to go through all the steps of solving this because we've done that, but if I max is 4.4, remember I max is E over R, or 22 over 5. That's 4.4. So if 1 is equal to 4.4 times the exponential, and if you think about this, R over L is 1.25, 5 over 4, then we can just solve this for the time. And if you want to pause and slog through this, I invite you to. I'm not going to write out all the steps because we've done this, but the time is 0.215 seconds. Then what we can do is we can calculate di dt. And di dt is going to be equal to I max times the derivative of 1 times the derivative of negative e to the minus r over lt, which will be positive r over l e to the minus r over lt. We evaluate this at t equals 0.215 seconds, and we're going to get essentially a value of 4.08 amps per second. So the current is increasing at a rate of 4.08 amps per second when the current is 1 amp. So remember that di dt is a function of time. So I is increasing, but di dt is the slope of that, so it's decreasing. So then this is pretty easy, okay? We can plug in that the current is 1 and di dt is 4.08 and L is 4, so that means that the instantaneous rate that power is being stored is about 16.1 watts. Okay? All right. So we don't really need to worry about the negative sign because that's kind of irrelevant for the amount of power. And that's pretty much it. Okay. In the next video, we're going to talk about LC circuits, and we'll wrap up our discussion of electromagnetism by talking about RLC circuits.